Okay, let's try to evaluate this integral using trigonometric substitutions. So the first thing that you have to notice is that in this integral, uh, it's a definite integral that goes from 0 to pi over 2. And in the numerator, you have a constant. And in the denominator, you have an expression that involves trigonometric functions. So if you see something like this, the best way is to use a trigonometric substitution. So when it comes to a trigonometric substitution, I am talking about something like this. So we can use t equals tangent x over 2. So these are these half angle identities that you find in trigonometry. So if we draw a right angle triangle, let's say with this angle x over 2, then this is going to be t, and that's 1, right? Because tangent is defined as the opposite over adjacent, and then you can get the hypotenuse as t squared plus 1 squared, which is again 1. So from here, what we can do is we can define sine x over 2, which is going to be t over square root of t squared plus 1, and cosine x over 2. That's going to be 1 over square root of t squared plus 1. Now cosine t. So you can see there's a cosine x and a sine x. So we know from half angle identities, we can write sine x equals 2 times sine x over 2 cosine x over 2. So now we can substitute these expressions, if I call them 1 and 2, I can go ahead and substitute those. So I have 2 sine x over 2 is t over square root of t squared plus 1 multiplied by 1 over square root of t squared plus 1. So then I get sine x as 2t divided by t squared plus 1. Now similarly, so this is an important expression. I can call it number 3. Now similarly, what can we do is we can express cosine x. Cosine x can be written as cosine squared x over 2 minus sine squared x over 2. So these are again half angle identities that you come across in trigonometry. And then cosine squared x over 2 is simply 1 over, take the square of this number 2. So that's going to be 1 over t squared plus 1 minus sine squared x over 2, take the square of number 1. So that's going to get t squared t over t squared 1 plus 1. So then you can see we'll get 1 minus t squared plus 1, and I'll call that number 4. So from number 3 and number 4, we can substitute for our integral. Now we have to substitute for this dx in terms of t. So let's try to do that. So I'm going to write t equals tangent x over 2, because that's our initial trigonometric substitution. And I'm going to solve for x. So x over 2 is going to be inverse tangent t. And then x would be 2 times inverse tangent t. Now I'm going to take the the derivative of x with respect to t, dx over dt. So I have 2, and the derivative of inverse tangent t with respect to t is going to be 1 over 1 plus t squared. Okay, so then from here you have dx, that is our original differential, is equal to 2 over 1 plus t squared times dt, the new transformed derivative in terms of t. So we are going to use this along with number 3 and number 4. So I will call this number 5. And also look at the original upper limit and the lower limit. So these limits corresponds to x, but we have to convert them into t. So let's try to do that now. So I'll write two columns. So this is x and this is t. So when x equals 0, let's look at this substitution. So that's how we are going to find t. So 0 over 2 is 0 and tangent 0 is equal to 0. So when x equals 0, t will equal 0. When x equals pi over 2, when x equals pi over 2, I'm going to substitute pi over 2 here. So then the argument, the angle would be pi over 4. Tangent pi over 4 or tangent 45 degrees is going to be equal to 1. So that means t is going to be 1. So now with the help of this trigonometric substitution, t equals tangent x over 2, we have written sine x in terms of t. We have written cosine x in terms of t. We have transformed the differential dx into dt, as well as we have transformed the original upper and limit in terms of x to lower and upper limit in terms of t. So now we are ready to substitute for this integral, can transform it from x variables to t variables. So now let's try to do that, and then we'll move forward from there. Okay, now let's substitute for this original integral. The limits in terms of t would be 0 to 1, and our dx, I'll write 1 here, and our dx would be 2 times dt over 1 plus t squared, and then we have 3 plus 2 times cosine x. So instead of cosine x, I'm going to put that substitution 1 minus t squared divided by 1 plus t squared. Then I have plus a 2t, so sine x would be 2t over 1 plus t squared. Okay, so that's going to be that, and then let's try to simplify this further. So if we simplify this, I'm going to start from here. I have a 2 there, which is a constant, so I'm going to take it outside the integral, 0 to 1. I have dt, and then in the denominator, I have 3 plus 3t squared plus 2 minus 2t squared plus 2t. Okay, and then you can see there's going to be a common denominator. That's going to be 1 plus t squared, but this common denominator can cancel out with this one. Okay, so that will cancel with that one, and then we have 2 times 0 to 1 dt, and then we have t squared plus 2t plus 5. Now in the denominator, you have a quadratic expression in t, And if you look at the discriminant of this quadratic expression, that's going to be less than 0, or it's going to be a negative value. So in that case, the best way to solve this is to complete the square of this quadratic expression. So I'm going to do that now. 2 from 0 to 1, and then we have dt t plus 1 squared, and then we'll have a 4. Okay, now you should know that 4 can be written as 2 squared, so I'll write it like that, 2 squared. Okay, so this is what we have, and now we have to integrate this expression. So if you recall an integration identity, like for example, if you have this one, this is a side note. Let's say that you have dt over t squared plus a squared, and you have to integrate it with respect to t. Then the answer here would be 1 over the square root of this constant times inverse tangent t over a plus a constant. Okay, so that's the expression we are going to use here. So you can see, if I use this identity, I'm going to have a 2, the original 2, and then you can see 2 squared, so I will square 2 squared, which is going to be 2. So I'll divide this by 2, and then I have inverse tangent t plus 1, because you can see if it's t squared, then I put t, but here it's t plus 1 squared, so I had to put t plus 1 over the square root of this constant over here, which is 2. Okay, and then what I'm going to do is that I will take the limits of this from 0 to 1. So let's try to complete it over here. So I can take the 2 1/2 outside, and that will cancel with the 1 over here. So then I'm going to substitute the limits, the upper limit, inverse tangent. I will have 1 plus 1, so that is 2 over 2, minus inverse tangent. I'll have 1 over 2. So I have 1 over 2 here. And then inverse tangent 2 over 2 or 1 is basically pi over 4, pi over 4 radians. So I have pi over 4 minus inverse tangent 1/2. So this is going to be the final answer for this problem. If you want, you can get a numerical value by taking the numerical value of this inverse tangent function, but I'm going to keep it like this. So we have pi over 4 minus inverse tangent 1/2 would be the answer for this integral. So this is how you do this problem.